have lots of properties. We can probably, well, I'll show you. Our time is running low, so speed it up. Okay. So, given that, at least in the case of k equals 2, we can talk about some of the identities that Maple found and that I helped it find. I wrote these down.
Are they proved or only conjectural?
Most are proved.
That's
Some are conjectural.
Conjectural are better proved.
So, we'll start. Let's see how much time. I got time. All right, so let's see. So let's start with some easy ones. So an easy one to show. So these are our Maple discoveries. I'd like to take the credit. All right. So the first one is, and this one actually you can just read off from this formula if you think about it a little bit, is that, well, let me introduce notation, then I'll give you the actual identity. So we care about sequences of the following form. So we'll have the sum of characters. All right. So this may be a multi-partition, as will be this. And then we'll raise it to some power r. But we'll keep mu fixed, and we'll let lambda vary. We could do it the other way as well. And this will be a partition, let's say, of n. But we'll want to bound some of them. These produce really interesting sequences. So we'll bound the length of lambda by some parameter. And so for now, I'll call this a, I'll put the bound, the power, and then mu. But I'll remove the ornaments when we just talk about specific ones. Okay, great. So for the symmetric group, there's some really nice ones. So for example, B could be infinity, so they could be unbounded as well. But then we know what those are, just threw it out. They're not interesting. Not that interesting. So one of the interesting ones that comes up is A. So instead of N, I might put the group, because it might be HN or SN. So I'll put the group. So A, and let's just take the squares. Okay. SN. And let's bound them by 2. So these are all of you take the sum over all the characters, a squared sum, such that this has at most 2 rows. Lambda has at most 2 rows. And this thing is a well-known sequence. These are the so-called Catalan ones. Okay, so this is, everybody knows. All right, fine. And so these feature prominently all over the place in the character tables of SN, and they will also feature prominently in the character tables and the sequences for HN as well. And we'll see why. Okay, so this was just an example. So now let me give you something that follows from the formula, but Maple showed me. So one is that if we take AR of SN, some bound B, and some element, some partition mu, this is the same thing as AR of HN, where we take the same data, just append a 0. So I discovered this. This is nice. Why is this nice? Because it allows us to express recurrences for the character table of HN in terms of these values for the characters of SN. Okay, this is the point. And because we know this, we can bound the degrees of these recurrences and so on and so forth. It's great. Okay. So some of the early ones that Maple found, but also well known, I'll skip because they're well known. So I'll give you the new ones. My time's running out. So in general, let's say we have the following matrix. So here. So if we fix mu to be identity, okay, and we'll fix mu to be identity, we'll fix R, and we'll consider the bounds. So I won't write R.
You mean all ones?
Yes. So these look like this. 0. And so actually we're only going to do the hyperoctahedral group. Then we get a formula, explicit formula. So we get Aij of n, I'm omitting the R, is equal to, so I'll put n here, the sum of ai0 at k, so it's this sort of convolution of I0 and J0 times n choose k to the rth power, and this sum just ranges from k equals 0 to n. Explicit formula for all. This is an infinite family of identities, just based on these things, which are symmetric group ones. Okay, symmetric group identities. And there's a semi-closed form, determinantal formula, that gives you these things. So you have tons of them. Okay. So one of them, all right, since my time's almost up. Since I noticed that next week's talk is going to be on pattern avoiding permutations, one of these counts a restricted class of pattern avoiding permutations. And so, talking about it right now. So one of them is this. So I have to introduce some notation first. Okay. So let sigma be an element of Sn, and write sigma in one line notation. Okay, so this simply means that this is the permutation that takes 1 to A1, 2 to A2, and so on. Then the reverse of sigma will just be the reverse of this word. A and A minus 1. Then the complement of sigma will just be the complement of each one, where by complement I mean AI maps to n minus AI plus 1. So it's what you think it would be. Great. Now, take all the words, or rather, take all the permutations. So consider only permutations sigma such that they are invariant under the reverse complement map, so compose them. Okay. An example of this is, 1, 3, 2, and then this would be 5, 4, 6. This works. Okay. Now, it turns out that there is an explicit formula to count the number of monotone increasing subsequences. So you can take a subword just by dropping elements. And you can count how many that avoid a certain length of monotone increasing subsequences. Okay. And let's call this, so B2n. But in this case, there's a formula for 2n and there's a different formula for odd. And so this will be this, and let's say increasing 1 through k. So this is number of permutations invariant under RC invariant, that avoid, in other words, they don't have a subsequence that increases of length k, avoids 1 to k. And the formula is given by these things, right? And it's actually a k plus 1, so k is this, over 2 minus 1, k plus 1, so floor function, k plus 1 over 2 minus 1. It's this nice one. And I'm good. This is proven, this is true. But the method that came up with the formula is not one that uses bipartitions. In fact, it's a bit long. So I think I have a method of going directly from bipartitions to the formulas. That would be different in Thank you very much.